Welcome to the webinar, Removing Iron and Manganese from Well Water. I'm Cliff Tryons, Director of General Public Outreach for the National Groundwater Association. It is my privilege to introduce our presenter, Roger Miller of Water Systems Engineering in Ottawa, Kansas. Mr. Miller has more than 35 years' experience in multiple areas of the water industry. His work has involved research and development, project oversight, and technical training for managers of water systems. During the presentation, feel free to type questions in the question box. At the conclusion of Mr. Miller's presentation, he will answer your questions. Also at the conclusion of the presentation, we will make a handout of Mr. Miller's presentation available for downloading. So without further delay, I'll turn it over to you, Roger.
Thank you, Cliff. I appreciate it, and welcome to everyone to join the webinar today and talk a little bit about iron and manganese in our well water. We're going to kind of go through what they are, where they come from, the issues they present to us, and some of the resolutions we have available for iron and manganese in our well water systems. Iron and manganese are actually present in the subsurface in the earth as minerals, or what we consider metals in the subsurface. Pretty common and natural to the environment down there, very available to us, not only in solubilizing and becoming issues in our water supply, but of course for a variety of applications that we use both iron and manganese in our daily lives. Starting with iron, iron is a metal or a mineral that's found in the surface. It makes up about 5% of the Earth's crust. Doesn't seem like a lot of available iron in the world, but certainly that is a magnitude of available iron. We use it predominantly when we think about iron. It's the main constituent of steel, that and carbon and nickel. However, that the availability from the mining of iron presents that we actually construct our water wells. Not all of them of steel, but a majority of them are made of a steel product, so we actually have the availability of iron solubilizing within the water well, along with the natural available iron from the geological formations and the subsurface. So iron's a big part of what we deal with in the groundwater industry. The second component that we're talking about today is manganese, also a metal, mineral, a little bit similar to iron in appearance, as you can see by the two photographs here on the left. When we look at it under the microscope in the laboratory, we can see some very similar aspects of it. Manganese is a little different in what it presents as far as how we use it. It's a very brittle material. In fact, too brittle to be used alone, so it is used in the steel industry generally as an alloy, generally as part of a component, giving standard steel more of a strength factor. And I threw in a photograph of the soft drink industry where they use aluminum cans. They actually use a small amount of manganese in aluminum alloys to give it strength because they want to use such a thin-walled application. So two metals that are predominant not only in our Earth's crust and available to us, but in our daily lives. As I said earlier, iron makes up about 5% of the Earth's crust, and manganese makes up about 1/10 of 1% of the Earth's crust. So when you think about the subsurface where our groundwater comes from, the availability is, I guess you'd say, everywhere. Both metals are commonly found in the subsurface, naturally occurring, and the solubilization and into the water comes from a reaction we call the water-rock reaction or application. The general formations of iron that are, I guess, the two prominent ones in the subsurface are hematite and magnetite. And for manganese, the pyrolusite is a common rock that we would find if we went down into the earth and looked around. And what happens is the action of the groundwater flowing through these geological structures has a tendency over time to solubilize or bring very minute structures of iron and manganese into the flowing water. And that's kind of where it all comes from. Quoting a 2009 study, in the United States, all across the country, it was found that iron and manganese are found in just about 50% of the wells that were sampled in some detectable level. So showing you that just about everywhere in the country, if we drilled a water well, we would probably find about half of the time the presence of iron and manganese. So looking at the kind of problems that we probably will experience when we have iron and manganese in our water system, I think the biggest one that I see in our laboratory is the aspect of water color. As you can see here coming out of the sink, it's not very attractive from the aesthetic point of view, but certainly they can also cause taste issues, and in some problematic conditions, you may generate an odor, not so much from iron, but maybe some from a higher level of manganese and enveloped in various structures. I threw in the picture on the right, which is what we would call organically bound iron oxides. And this is kind of a component of the biological formation, or what you hear us talk about, biofilm, where the bacteria have actually taken iron and oxidized it into little rust particles and incorporated it into the polysaccharide slime that they secrete. So what you can get from that, as you can imagine by looking at that deposit, you can get fouling in your well and lost capacity. We're not going to really get into that area of the iron presence in your well today. I think we're going to have some future webinars talking about well fouling and what it means to us and how we'll handle it. But I wanted to throw that in just to let you know that iron is also a part of the issues of block flow and lost capacities in the well. When we look at iron, I think this picture depicts mostly what I'm talking about in water color. This is some samples received in our laboratory, the one on the left being, as you can see, red water. And that's what we mostly hear as a complaint on water quality or water aesthetics when iron is involved, is that orangish red water produced. A lot of times it's produced when the well starts up because it has a tendency to concentrate in the well borehole, and then when you fire on the pump, the first slug of water can be generally a red water, and it will generally dissipate over pumping time. But that's the problem that we have with iron. Looking at manganese, of course, manganese and iron predominantly are essential nutrients to our body. Manganese definitely is part of our need from an elemental standpoint. And what we showed here in this diagram was that it comes from a variety of the food sources that we have. But again, it also comes from our water supply, like most of our minerals that we have in our daily lives. Manganese being a little more of a fine-tuned essential mineral than iron, recent studies indicate that there may be some adverse health effects predominantly linked to cancer that can be caused from overdoses or overexposure to manganese. There's been a lot of studies of recent trying to identify the levels of manganese and, of course, the contact time or the years that somebody might have been exposed to that. But being a required and an essential element to our life and our body function, it presents a fine line for us in the water industry. There was also a study in 2010 that evaluated children exposed to a high concentration of manganese in their drinking water from groundwater supply source compared to those who were drinking a low level of exposure to manganese. And of course, the initial group performed worse on the testing of intellectual functions. So there's some, I guess you'd say, consideration of those aspects associated with overexposure to manganese. But I'd have to say, from my standpoint as a chemist, those are extreme measures over a long period of time, and that they're being monitored by the Health Association and certainly from the EPA standpoint as far as health issues. Nevertheless, the U.S. EPA, Environmental Protection Agency, has not set what we consider a maximum contaminant level for iron or manganese as a health risk in our industry. what we have in our industry are primary drinking water regulations. Those are regulated. And then we have secondary drinking water regulations. And right now, the EPA has placed the iron and manganese maximum contaminant levels for municipal water into the secondary category, which are really recommendations as to levels that may present some aesthetic considerations if you exceed those levels. So they're not in the primary regulations, which require you to do certain things if you have excessive concentrations, but they're in a recommended area where we might have need to watch them and avoid the aesthetic issues, predominantly taste, odor, and color that we talked about earlier. So looking at the secondary maximum contaminant levels, SMCLs, for iron would be 300 micrograms per liter of water. And to give you a little bit of a relationship to that, that is parts per billion. So if you had 1 gallon in a billion gallons, that would be that ratio. In the water industry, we pretty much discuss it as parts per million. So that would be 0.3 parts per million of iron and 50 micrograms per liter of manganese, which would be 0.05 parts per million. So not real high concentrations are required, and these are predominantly for the aesthetics of staining and taste, not so much odor even associated with that. Again, the 50 parts per billion of manganese showing that you would have at least the beginnings of some of these aesthetic issues. So what are we going to look at when we have iron above the secondary maximum contaminant levels? Mostly you're going to have that unpleasant metallic taste. I think that most of us would be able to detect that if we had that concentration, if we were not used to drinking that kind of water. So once you drink a water that contains maybe a maximum contaminant level or above, you would get used to that taste, but it's a metallic taste that you would have. I think the biggest thing from iron would be the iron staining, and it's pretty predominant when you have iron above that half to even a part per million in your flowing water. And you can see here it's going to stain your white clothes specifically in the laundry. You're going to have stains in your toilet and toilet bowl, so they're going to be very visible to us in our daily lives. And of course in our sinks and other surfaces where the water may stand for a while, that iron is going to precipitate out and stain those surfaces. So we'd be very aware of the fact that we have an iron issue. So higher iron water predominantly is going to cause us that metal taste and certainly the staining. Manganese being exactly the same, an unpleasant metallic taste. However, this taste from manganese is much more bitter and stronger than the metallic taste from iron. I think you would probably realize that anytime you would drink water that was excessive concentration of manganese. And the staining issues are considerably worse. As you can see, the stain of manganese is black. We would again find it anywhere in the toilets or the sinks where manganese water would have a tendency to stay and allow the taste. In our laboratory, when we have a sample that is dark gray or even black right off the bat, before we run any analysis, we realize that we're probably dealing in high manganese concentrations. So looking at that, iron and manganese certainly are natural constituents of the Earth's crust. They're metals or minerals. They come from the water-rock relationship. They present issues of mostly aesthetic value, taste, odor, and color. So what do we do about these problems when we have them in our water system? Number one, we can explore with a qualified water system professional the feasibility of maybe retrofitting our wells so that we can bypass any metal producing zones. This application would be very specific to an issue that we knew or were able to evaluate, that certain flow areas of the well were producing the iron and manganese concentrations. However, if we didn't know that, and it may take some evaluations through either literature search to know that wells in the area at certain depths provided high iron and manganese. But if we knew that, we could actually have a well professional come in and look at the feasibility of blocking that producing area of the formation and not allowing water to come in from that formation, which would then either reduce or eliminate the concentration of iron or manganese in our water well. Secondly, of course, would be in the aspect of drilling a new well and constructing a new well. If we knew and did our homework in designing and constructing the well, and we knew where the zones of high iron and manganese are, then we could design and construct the well, alleviating those areas as being producing zones into our well. So pretty unique when we look at the subsurface and the geology and the hydrology of the well system, where we could either blanket off if it's an existing well or design and construct around it if it's a new well. So two applications that we could look to resolving iron and manganese in our water. Third one, of course, would be the installation of water treatment technologies at the surface. And basically, when we look at water treatment for iron and manganese control or removal, looking at the two most common that I'm going to go over here today would be, number one, ion exchange. And I think a lot of us are familiar with water softeners. A lot of homes in today have water softeners installed in them, and this is a typical ion exchange technology. And what we're thinking here, or what we want to think here, is when we're looking at ions in water, we're talking about totally dissolved iron or manganese. So you're probably not going to see this as far as red water or even gray water is concerned. So it's lower levels of what we call soluble or dissolved iron or manganese in our water. The process is, as far as ion exchange, is that the water flows through a bed of resin beads, and the resin beads are charged with a specific charge. So what happens is the iron or manganese ion are then exchanged for a similar ion on the resin and therefore removed from the flowing water. Ion exchange. The magnitude of iron in the water applicable to a water softener or an ion exchange water treatment system is only about 2 milligrams per liter. So if you had more iron in your aquifer water when you tested it, and you were looking at a water treatment program, this wouldn't be the application because you would overwhelm the resin bed by the extra iron that you had. Or if you had a lot of particulate or solids in your water, probably ion exchange would not be a good fit. But otherwise, it's a very effective, ion exchange is a very effective and fairly cost-effective method of iron and manganese removal. The other system of the two most common systems is what we call oxidation and filtration. A brief explanation of that is the most insoluble phase of iron or manganese is the most oxidized phase. So as we oxidize our water, the iron and manganese become less soluble and more likely to, number one, form bigger particulates, or number two, to even precipitate out, making them much easier to filter in a standard sand and gravel type filter application. This is probably the most common iron and manganese filtration or removal technology, even through the municipal water plants, to the point where some iron and manganese filtration systems use a media that the oxidation chemistry is actually coated on top of the sand particles, so you get the oxidation of the iron and manganese in the same time you're filtering out the particulate. So oxidation and filtration being a very common use of water treatment technology in the industry. So looking at that, how can we handle the problems of iron and manganese? Number one, if we have an existing well and we know or can find out that certain zones are producing the higher iron and manganese, we can basically line the well and block off those areas of flow. Number two, if we're considering a new well and we do our homework and know the hydrological and geological issues in that aquifer, we can design and construct the well to alleviate the available high iron and manganese concentrations. And number 3, we can install the proper water treatment systems within our home to alleviate the problems. So to learn more about the selection and installation of home water treatment systems, a couple websites, the Water Quality Association, www.wqa.org, or the National Sanitation Foundation, NSF, which is nsf.org. We can find water treatment professionals, the certified water treatment professionals, and the certified products all through various areas within our water industry. From the standpoint of www.wellowners.org, the website that's probably the best tool we have in the industry to find out more about useful well owner tools, including private well owner hotline, private well owner tip sheets, online well owner lessons, and more webinars such as we're doing today. And we have on that same website, wellowner.org, online lessons. If you have questions like, what should I test my water for? How should I maintain my well? How can I help keep my water safe? What should I do if my well floods? Pretty important in today's world where we're flooding everywhere. How do I get water treatment? And what should I know about getting a new well? We have today covered one of our webinars, and we have another one. We'd like you to join us on the 18th next week, same time frame, for removing problematic fluoride from residential water wells. And on October 25th, water treatment systems maintenance basics. You can register on the site shown here below. So for questions, as Cliff said earlier, you can click on questions and type in a question and hit the send button, and we will try our hardest to give you the best answer that we can come up with. So Cliff, I turn this back over to you. I think you're going to be handling the questions.
Right, thanks, Roger. I want to emphasize too, go ahead and type in your questions now, because I know from having handled hundreds of well owner calls over the years that iron is something that a lot of people deal with and struggle with. So we're here to help if we can. Okay, I do have a question. First question is, it sounds like manganese can cause health problems. Why hasn't the EPA set a limit on it?
That's a good question. We in our laboratory, we followed this for a number of years, and the EPA does have a what is called a contaminant candidate list, and manganese has been on that list for some time now. So I guess I would have to say the answer that I have to that is that even though they haven't stipulated a regulation, they are continuing to evaluate that as high on the contaminant candidate list. And I think one of the issues that we have with manganese is, like I said earlier, it is an essential element of our body's function. So we need manganese, so the total elimination from manganese in our environment, and certainly our food sources and our water, would be a negative. So I think they're struggling with where they should put those limits and goals. But you know, I want everybody to know that it is not on the back burner. It certainly is on the front burner with the EPA, and as we've seen regulations change over the last 3 to 5 years, I would expect maybe there to be some definite controls on manganese. So hope that answered the question.
Okay, yes, we have another question, and this might be an opportunity to elaborate a little bit on the iron bacteria. The viewer says, I have read up on some iron slime issues, which I understand to be a bacteria. Can this be linked to high iron levels? So I guess is asking, what is the relationship between the bacteria and the iron levels, and maybe you can help flesh out the distinction between that and what we've been talking about.
Yeah, the groundwater issues of bacteria are really immense when we start to look at it, but there's a whole magnitude of microorganisms, and of course the world runs on microbiology, so it's nothing abnormal. But in the subsurface there is a whole group of organisms that we refer to as iron-related bacteria. What we call true iron bacteria are the ones that, by oxidizing the iron, by changing the elemental state of iron, they actually gain their life source energy. And so they produce a lot of these little particles of rust, along with other organisms that do that. They don't live off of the energy they derive from it, but they do that. So we have a lot of what we call iron-related bacteria. They're all natural to the subsurface. They're all natural in our source water. And what happens in a water well application, we set up an environment where we're flowing water, bringing nutrients every day to their lifestyle. We allow them to have, I guess, a good place to set up and grow. And in that process, they secrete what we call exopolymer or polysaccharide slime, and that's part of the way they protect themselves. And in that, they incorporate those little particles of rust. So that's why I was saying it's organically bound iron that's bound up in that biomass, that slimy material. There is some correlation to the concentration of iron to if you have an excessive presence of iron bacteria, only because they're going to concentrate that iron right around the borehole of the well. But iron bacteria can set up about anywhere as long as there's any soluble iron available to them. So if you have very low levels of soluble iron in the natural aquifer water, they can still over time build up that mass of iron biofilm or slime around the well and affect the concentration that would come into your home as your flowing water source. Secondly, they also can degrade any metal surfaces in the well. So if we constructed the well of a steel casing and screen construction, which a lot of our older wells and certainly many in today's wells are, that can also be a source of iron from their natural lifestyle process of oxidizing iron. So there's definitely a relationship and can be enhanced by the presence of iron bacteria. But also we can have just that natural water-rock relationship to produce a high level of iron. That's kind of a very brief overview of the bacterial involvement in the iron and manganese presence of groundwater.
Okay, thanks. Viewer asks, will treating with chlorine have any effect on iron levels?
The deal with chlorine is it's definitely an oxidizer. It's an oxidizing biocide. In fact, in municipal water treatment, a lot of the methodologies that we use to oxidize soluble iron into that insoluble state and be able to filter it out, we do with chlorine. The only issue with chlorine in a water well structure is the potential of it oxidizing and maybe even having an effect on the steel construction of the well itself. But that takes a considerable amount of contact time over many years to produce any kind of degradation. Otherwise, using chlorine to control the bacteria in the well, which is generally the use we would have, would really be beneficial if we're filtering the iron, because it's going to oxidize it into an insoluble state, and it's going to fall out either, if we have any kind of filtration or really any kind of retention. So if we have a pressure tank or anything like that, we would really allow the iron to move to that insoluble state and drop out of solution. So no, it's not really a bad process as far as iron. The only issue, like I say, is if you put chlorine down your well and you had a steel constructed well and you just left it down there forever, it could be somewhat corrosive to the metal structure of the well. So anytime you disinfect your well with chlorine, you don't want to leave it down in the well for a long period of time.
Thanks, Roger. I just wanted to interject here real quick, since I have responded to a lot of calls about the use of chlorine. The National Groundwater Association does not recommend that people use household bleach for a chlorine source because it's not designed to be used in drinking water, and it degrades pretty quickly, has a very short shelf life. So there are other forms of disinfectant that can be used. We recommend that if at all possible, you use a groundwater professional to disinfect well systems, because there are many steps to the process and they need to be done properly in order for effective disinfection to take place. But I know a lot of people equate chlorine to bleach, and that's not what we recommend you use, the bleach. Okay, I have a question about where do I go to get my water tested. So if somebody decides, I think I need to see how many parts per billion of iron I have in my well, how would they go about getting that done?
Well, I think number one, my experience is the county health department generally is a good place, a good source. A lot of states have different controlling organizations, Department of Natural Resources, or any of those. Some have testing laboratories which are run by the state. I think on our website, if I'm correct, Cliff, we do have some areas where they can get information on testing, but general testing laboratories and generally state laboratories are the ones that I would recommend. Yeah.
Okay, yeah, we do on our wellowner.org website. If you go under the water quality section, it can guide you to somebody who can tell you, or you can find the certified drinking water testing labs in your state. Okay. Let's see. Okay, I think you addressed this question somewhat, but I'll give you another chance if you want to elaborate. Why would I choose ion exchange over the other method, oxidation and filtration? So you talked about choosing oxidation and filtration over ion exchange, but why might one want ion exchange if it treats at that level?
I think ion exchange in low concentrations of soluble iron and manganese would be a good approach, I guess I'd say. And what I say is a lot of times you might have levels of iron and manganese down in that 1 or 2 parts per million that you're not going to see so much at that level. You're not going to have that red water. And if you didn't have a lot of what I would call particulate in your water, in other words, if you poured a glass full of your water out of your well and let it sit for a while, do you have any metal particulate or settling in the bottom of the glass? When those things are not a problem to you, ion exchange really is a good technology. It's fairly easy to operate. If anyone who owns a water softener, you just have to recharge periodically with salt water, and so you do have a fairly low maintenance application. I'm not totally familiar of the capital equipment cost compared to a oxidation and filtration type setup for a homeowner, but I think from the standpoint of a low level of dissolved iron or manganese in your system with very little particulate in your water, really iron and manganese, or ion exchange would be an excellent method. It's very effective, and in reality it's a good cleanup process. What we see in many times, especially in groundwater, is that we may exceed that level of iron and manganese that limits the ion exchange technology, and we also might have what we call too much suspended or dissolved solids, which will foul up an ion exchange system much easier than it would an oxidation and filtration system. So I think there are times when you'd have iron and manganese at levels that really ion exchange would probably be effective in the removal and would be maybe a little less of maintenance cost from the standpoint of regenerating the ion resin. So that'd be kind of where I think that might fit.
All right, thanks, Roger. We had the one viewer ask if they would be, if they're able to download the slides, and the answer is yes. If you look in your little panel, you'll see a place that says handouts, and there will be a link there you can click on to download the presentation. Have another question. If it is an option, is drilling a deeper well the preferred long-term solution for mitigation versus treatment?
You know, from the standpoint, and I guess that again would also depend on how deep you had to go. Certainly, if you went to a lower aquifer area that did not have high iron and manganese, that would be, I guess you'd say, quote unquote, a permanent fix. So that would be a fixed cost, where if you install water treatment, you do have, you know, annual maintenance cost and typical regeneration cost of either, you know, the salt water or the ion exchange resin regeneration. So, you know, based on the typical life of the well and the cost of how much further you'd have to go, you know, that would be an evaluation you'd have to look at from that standpoint. But I guess the benefit of, like you say, trying to hit an aquifer that has acceptable levels would be based on how far you'd have to go and the drilling construction costs from going down that far. I've always wondered about, you know, if that's effective, if there's a level of depth in construction, and I don't think you can really evaluate it. And you know, it's almost like a site-specific application, but it could be beneficial in certain situations because that would be a permanent fix for the higher concentration. So, hope that answers the question. Yeah.
Okay, thank you. Question: Will a carbon filter, like the kind you put on a tap, remove iron?
To a degree, it will certainly remove the iron particulate, and the only problem with that, you know, insoluble iron could be, you know, below the secondary maximum contaminant level anyway. So it would be, I guess you'd say, somewhat, and probably to most people would be an acceptable removal process. The problem with that is the unsoluble iron, the particulate, these little particles of what I'm going to call rust, would, if they're extreme, would certainly foul up a small carbon filter, generally like at the point of use tap application. So you might have filter replacement issues a little quicker than you would desire, but yeah, it would remove the higher iron levels and probably be acceptable to you. I just question the aspect of how often you might have to change those filters, because carbon's basically established for taste and odor rather than actual particle, but it would remove the particles of iron, yes, or manganese, yeah.
I want to add, there's another question that's similar. I'm going to kind of reframe, but there are other types of filters, like I've heard of sediment filters and other types of filters to take particulate out of the water coming into the house. Would this be the problem you just described of filters getting clogged? Would this be a problem with other types of filter other than a tap-mounted carbon filter, but any filter that's filtering out particulate could get clogged up depending on how much iron is in the water?
Yeah, I think that the uniqueness there is that a lot of filters that are what we call particle filters or particulate filters are actually designed to trap larger volumes of sediment or particles before they would be fouled to the point of needing to be replaced. And most of them are, you know, wound filament type of cartridges for sediment trapping or filtration. Where carbon, like I say, it's generally a ground up carbon source in a cylinder, and the water flows through there. And like I say, carbon filters are specific applications or taste and odor. They're going to absorb, you know, whatever's causing a foul taste or foul odor in the water. In that process, they also will absorb whatever particulate they can have available to them. So I think just the two different technologies of ground carbon versus filament wound. Filament wound, it has much larger pore spaces and therefore can trap a lot more sediment before it would be considered saturated and need to be replaced. I think, yeah, it's kind of a, you know, two-phase application. One's actually made for another process, but would trap particles, but would foul sooner, where filament type filament type filters they're kind of designed for that, and they have longer lives before they're saturated. Absolutely.
Okay, thanks. Question: does treating for iron automatically treat for manganese as well, and vice versa? So,
yeah, generally in these processes we're talking about as ion exchange and oxidation filtration, those two minerals or metals definitely react the same way. Once they've been oxidized into that higher state, they are more susceptible to falling out of solution or being filtered. I think ion exchange probably is a little more effective on iron than it would be on manganese, but yeah, the general process of the two types of water treatment we discussed here today would be similar for iron or manganese.
Okay, thanks. I have a couple more questions relating to fouling. How do I know if I have fouling in my well system, and what is involved in getting rid of it?
I think generally, you know, of course, there's a variety of different indications that your well is fouling. Number one, of course, would be what we call loss capacity or loss of flow. So if your well was not able to produce the flow that it initially did, that's generally caused from a lot of the flow paths in the well design are being blocked by fouling, and that can be mineral precipitation or biological deposition. So if your well slows down from the standpoint of not producing water as rapidly as it used to, of course that could be a pump problem, but if you had that pump problem evaluated, the other process would be fouling. And the other way would of course be is if you had your pump pulled for a service application and you had a lot of material built up on the pump itself, either biological slime as we talked about earlier, or mineral precipitation like calcium carbonate, that white buildup that we see around our sink faucets. That's a typical water-based mineral. Or even some of the iron oxide, the little rust particles built up on the pump, then that would be indications that your well proper itself is fouling, and you're going to be causing not only problems of water quality and aesthetics, but of course loss capacity. So I think those are the two driving factors that we look at in the industry. Is the well producing the water that it used to? Is it getting worse all the time? And then if we have any kind of visual ability, like pulling the pump, and what do we see built up on the pump when we bring it out of the well? Is there any kind of material built up on that? Because if it's on the pump, it's going to be out in the gravel pack in the screened area where the water comes into the well also. So I think those are the two major drivers for that.
Okay, you mentioned earlier about iron not being a health hazard, but this question asks, is iron fouling dangerous to my health? That slime I've heard about doesn't sound good.
From the standpoint of the controls that we have on our water in today's world, the only issue that would come into play there would be what we call total organic carbon, and that's really not so much of the health driver, and that generally is pretty heavily adhered to the surface of the well. So in reality, the availability or the presence of biofilm or bioslime is not really an issue as far as the material itself being a carbon-based polysaccharide type material. What happens, and I guess the problem that we would face, and I know we'll probably discuss this in future webinars, is the controlled health aspects of in that bacterial slime. Is there pathogenic organisms? In other words, are there bacteria that will cause me problems and that are controlled by our regulations. So can be a problem if that's the case, but in most cases, a lot of producing water wells, even our big municipal water wells, have a strong presence of organic slime and bacterial buildup, and are not in the process of being a risk to our health, and certainly not through any regulatory issues, unless they have the presence of pathogenic organisms. So I guess to answer that question directly, there's really not a health issue with just biofouling or the presence of the bacterial slime, but the potential increases as that slime becomes more prolific in the well, in that eventually the pathogenic organisms could be present. So kind of how the regulations fit and really the health risk fit there.
Okay, thanks. I want to encourage people to type in their questions. We've got one question left, but if you've got more, type them in now and we'll go ahead and field those. We're on for another 15 minutes or so. This question is, can you clarify two things? First, how can I find someone to install treatment equipment? And second, how do I know the system works?
I think, Cliff, I think you may be better fitted from the NGWA standpoint and maybe answering those questions. If you'd take that, I appreciate it. Sure.
Well, we do have some information on this on our wellowner.org website, but basically the Water Quality Association represents people who manufacture, sell, and install and maintain home water treatment systems, and so their website, I believe, does have a service on it where you can look up people that are probably members of their association or certified by them. So that's one way you can find somebody who installs and sells systems. Also, the Water Quality Association has that division. It's an independent product testing lab, as is the NSF, National Sanitation Foundation. And so they will independently test products to see if they treat what they purport to treat at the levels that are effective. And so we recommend on our wellowner.org website that if you're considering purchasing treatment for specific things such as iron or manganese, could be anything else, arsenic, whatever, that you take your lab result in with you when you go to look at these treatment systems, and that way you will have a very precise laboratory result that you can compare against this product specifications to determine if, in fact, that system has been independently tested to be effective for what you need. And both NSF and, I believe, Water Quality Association on their websites have places where you can go to look up certified treatment products or systems for the needs that you have. So it's a way of, you can do a little homework on the front end, but we really encourage well owners in all the materials we put together to take the little bit of time necessary to inform yourselves about what it is that is problematic in your water quality, and then do a little research on the products to treat it and who are the people out there that can install and maintain these systems, because maintenance is something that is often overlooked. They install a system and then they don't pay too much attention to the maintenance schedule, and if you wait too long, it's just like a car. If you wait too long in that oil filter, you could have a problem. So those are two sources. And then I would just throw in one more thing. It was referenced there earlier about how you could retrofit an existing well or maybe drill your well deeper. If you want to find a water well system professional to discuss these options with, wellowner.org has a service called Contractor Lookup, where you can find National Groundwater Association members or professionals certified by our association in your area. So that's a good question, because a lot of people want to do something, but they're not quite sure how to move forward. Roger, I think we're at the end of our questions. Is there anything you would like to just remind people about here before we close out?
Oh, I think you hit on a couple things there in information searches, I guess, is that the water well industry and National Groundwater Association, you know, we're all professionals in the industry and experienced in different areas. Our company is a forensics laboratory and problem solving. And iron and manganese, as Cliff said initially, issues in just about every groundwater system that you know, we have problems with. And so it's common, I think, getting involved, the right people in the organization, as Cliff mentioned, on disinfection of wells. I know we're working on some of those areas where we have some strong recommendations that well professionals be involved. And I think that's probably the one key that I would recommend for anybody on the webinar today or any of the discussions that we may have, is bringing in the professionals assures us that we're looking at the problems. We know where the problems are coming from, and we're selecting the right tool out of the toolbox to resolve the problem. So I guess I would emphasize that. I appreciate everybody being on the webinar today, and I certainly enjoyed being involved in it, and thanks a lot.
All right, thank you, Roger, and we want to thank everyone for joining us today. Have a good afternoon.